Yep, 1, 2, 3. Yeah, it's working, so I can get started. Yeah. Okay. Hello, everyone. My name is C. Chen, and I'm a PhD student at RMIT University. And I just finished my internship at BE Systems. And during this time, I work with Jeff, and we conduct some joint communication link tests. And basically, we did 3 tests targeting on Jones Wi-Fi link, telemetry link, and radio control links.
Before you go on, can I ask you to share your full screen? You're just sharing the slides.
Oh,
so, sorry to interrupt.
Yep.
So on the Google Hangouts.
Yep.
Just need to go. Need to share the full screen.
So this is the full screen. It means full screen.
Okay.
Yeah. And it's just hide. Yeah.
It's not actually working.
So where's my slide?
I might just have to go with this one because that's not your slides.
No.
Maybe can you go up? Yep.
Yep. All right. So this is overall diagram showing Jones communication links. Normally, Jones has 3 communication links. The first one is 2.4 gigahertz radio control link, which is used by Jones operator to change the Jones attitude angles and let it take off or land, disarm, or arm the drone. And the second channel is a telemetry data link. It's mainly used to monitor the drone's flight status. So, yeah. So people can use it to monitor drone's attitude angles and its speed and GPS locations. Also, this channel can be used to send the drone some commands. For example, you can use telemetry channel to let the drone take off and land. And the third communication channel is the radio, the video link is used to video streaming. And we have carried out 3 tests on the drone's Wi-Fi link, radio control link, and telemetry link.
Sorry, we're going to have to go with this one. You're going to have to open your slides again. And then sharing that screen. That's this one.
Yep.
What does that say? Full screen? Is there anything for full screen?
Full screen, no. It just said hide or stop sharing.
We'll have to go with that, Jeff. It doesn't have the option. So we'll just go with that. Is that okay? Is that okay, that one? Does that mean okay?
So that means cancel. So this means share?
Yep. We want to share.
You want to share?
Yeah. Because it wasn't following your slides. Okay, that's good.
All Alright, this is our first test. We conducted this test on Parrot AR drone, and this drone is controlled by an iOS or Android device via Wi-Fi, and it runs the Linux-based flight control firmware, and it has several weaknesses. So for example, its Wi-Fi has no encryption, and its Telnet and the FTP are enabled in the operating system with no password. And Sammy Kamka was the first person who made the hijacking software to hijack this AR drone, and our test was inspired by his project, and we did it in a different way. And so here's the attack steps. So Parrot company owns some unique MAC addresses. So for example, this MAC address starting with 9030B7 is owned by Parrot. So we're just scanning the MAC address of the surrounding devices. Once we find the MAC address like this, we know it's a Parrot device, and we know it's a AR drone.
Sorry, we're just not seeing the slides on the internet version.
Okay.
Sorry for the interruption.
So we want to go to screen.
So you just got to go to Google Hangouts. We've had every permutation and combination of Google Hangout issue today. So we have...
So this is my slides, and this is the full screen of the slide.
This may work.
Yeah, and then just hide it.
Just give it a second.
So
if we just go, I just go projector only. Extend. That's it? Is that correct? Yep. Yep.
okay,
Okay, apologies.
that's fine. All right. If you run the hacking software, we'll find the MAC address of the drone, and it matches with one of Parrot-owned MAC addresses. And also we find basically the AR drone is a Wi-Fi host, and it is paired with the iPad or Android device you use to control it. And the second step is to connect the hacker's laptop to the Parrot AR drone, and then acquire an IP address via DHCP. And here we can see the IP address assigned to the hacker's laptop is 1.3. And once we get this IP address, we can remotely log into the operating system running on the Parrot drone. And the IP address of the Parrot drone is always 1.2, 1.8, 1.1. So we can just use Telnet to remotely connect to the Parrot drone. And once we log into the operating system of the Parrot drone, we can deploy some new rules to the built-in firewall. The Parrot drone has a built-in firewall, so we can add new rules to the firewall to block all possible IP addresses other than the one used by the attacker's laptop. And the last step is to start robotic operating system on the attacker's laptop to manually control the drone. So, and also on the attacker's laptop, we can see the onboard camera's image. So this is an image taken by the onboard camera on the AR drone, and it's my garage door. And here's a video demonstrating how they perform this attack. So initially, the drone operator is connecting his control device to the AR drone. And then the attacker is running the hacking software to disconnect the drone from the drone operator's control device, and then block the drone operator's iPad, and it will prevent the iPad from reconnecting to the AR drone, and then the attacker will start a robotic operating system to manually take over, to manually control the drone, take over the control of the drone. And everything is done automatically. There's no human interaction required. And now the drone has been connected to the attacker's laptop, and we can see the image from the AR drone's onboard camera. And we can use our keyboard to control the drone. All right, let's have a look at the second drone communication link attack. The second one was targeting on a commercial drone's telemetry link. And Neil Roden was the first person to propose this type of attack. And but in his presentation or paper, we couldn't find much information about the specifications of the hardware or the drone he used. I did send him some emails, and I got some hints from him, and then I just did this test myself. And on the right, you can see a picture of the test setup. Here we have a target drone, and on the right way, there's the drone operators. That's a drone operator's ground station, and initially the drone is paired with the drone operator's ground station, and the drone operator can send a telemetry command to take off or land the drone, or he can also use the remote control transmitter to control the attitude and angle of the drone. And our aim is to show that we can remotely disconnect the drone from the drone operator, and then pair with the drone's XB radio, which is the telemetry communication hardware, and then take over the control of this drone. All right. As I said, the telecommunication hardware we use in this test are XB radios. And here I just briefly explain how two XB radios communicate with each other. So each XB radio has an MAC address. So in order to pair one XB radio to the other one, we just need to set its destination high address, DH, and the destination low address to be the same as the other XB's MAC address. So the other ones, DH and DL, are the same as the first one's MAC address. So initially, they're paired with each other. They can only talk with each other. And XB has three operating modes. The first one is AT transparent mode. And in this mode, XB is used as a remote series connector. So whatever it receives, it just pass to the laptop it's connected to. And the second mode is command mode, AT command mode. We use this mode to configure the parameters of the XB radio. And the third mode is API mode. We can do a lot of things using the API mode. But in this test, we use API mode to send the API command to remotely change the configuration of one XB radio. So we can change the DH or DL values remotely. All right, and this is the hardware connection on the drone, and it's a typical configuration for aero imagery drone. It has HK pilot flight controller, which is a clone flight controller, clone APM controller manufactured by Hobby King. And also, this drone is equipped with GPS, RC receivers, and EICs, and also XB radios for telecommunication. All right. So the first step of the attacks is to configure the XB radio in AT mode, and then we send ATND command to the network. Okay, so this command, it will be broadcasting to all the devices within the same network, and it will reveal the address of all devices in the network. So, and we have an assumption here is we know the personal area network ID. So all the devices in the network have the same PAN ID, and we assume that it's the default value is used. So we know this parameter, and so once we send this ATND command, we'll detect the drone's XB radio's address. So here is the XB radios on the drone XB radios DH and the DL address. And once we know this address, we can remotely change those values. Remember, I mentioned like in API mode, we can remotely change the hardware settings on the XB radio. So we just send an API command to remotely change the DH and the DL address to disconnect the drone from the drone operator, and then connect it to the attacker's ground station. And the third step is to change the attacker's XB radio into AT transparent mode to start receiving the data sent by the drone's XB. And the last step is to start the attacker's ground station software to start taking over the control of the drone. So as we can see, this is the interface of the attacker's ground station. We can see the drone's GPS location, and we can see the drone's attitude angles. More importantly, we can send some command. For example, we can remotely we can arm or disarm the drone. So once the attacker has taken over the drone, he can disarm the drone while it's flying. And here's the video I took. Okay, so initially the drone operator is starting the drone as normal, and he's not aware there's the attacker who is trying to take over the control of the drone. Initially, the drone's XB radio is paired with the drone operator's XB radio, so they can only talk with each other. The attacker is not able to detect the data. So now the drone operator is arming the drone using his ground station. Right. This is the first step of this attack. So now the attacker's ground station is paired with the drone, and the attacker can disarm the drone. Just imagine the drone is flying, and the attacker can suddenly stop the motors of the drone. And he can rearm the drone as well. All right. Okay. So the first test was conducted on the drone's radio control link, and in previous attack, there was an assumption, as I said, we assumed we know the pin ID, so it was set to the manufacturer's default value, and it makes the attack easier. And if we didn't know the pin ID, the attack would be much harder to perform. And in the third test, we have no idea we know nothing about the settings of the wireless communication hardware. So this test is harder than the previous one. And this attack was actually the group called the Positive Research Center run a contest of taking over a semi drone, and so they use two attack methods. One is using SDR, and the other way is using an RF24 wireless transmitter. And our work is our test is similar to their attack. But if you search for their contest, like I basically follow their instruction. They released a very detailed instruction showing you how to repeat this attack. But I found some mistakes they made in their code and in their hacking steps. Actually, if you follow the instruction, you won't get the result. And I have figured out how to fix those mistakes. And also, they performed the attack on a semi drone, and I did this test on a different drone platform. I performed this attack on a drone called Crazy Fly 1.0. Now they have released Crazy Fly 1.2. This is the older version, and this is an open source drone, nano drone, and this drone comes with a Crazy radio, which is used to send and receive the control signal to control the drone. And both Crazy Fly and the Crazy radio use NRF24L01 Plus as their wireless transceiver. And in this test, I have also used Adreno Mega to set up the NRF transmitter, and I also used a gamepad to manually control the drone. And here's the overall setup of this test, and it's similar to the second test. On the right, we have drone operator's ground station, and the drone operator used that to transmit control signal to the drone via this Crazy radio dongle, and then he can use this gamepad to control where he wants the drone to fly. And the attacker is going to use his ground station to detect the data sent by the drone operator. And on the right, this picture is the ground station's user interface. And similar to the mission planner, on this ground station, we can see the attitude angle and the reference attitude and the actual attitude angles. All right. So in order to receive the data from one NRF24L01 radio, one need to know three parameters. So we need to know the data package's address, and the radio communications channel, and also the air data rate. So we need to know all these three parameters. Always nice. Okay. Yeah, that's no means. Okay, and if we check the NRF24's document, we find that it operates at three different air data rates: 250 kilobits per second, 1 megabits per second, or 2 megabits per second. So there are only three possible air data rates. And regarding to the channels, maybe I just use it without it. I kept talking without it.
Maybe near the microphone.
Yep.
So let's see if I can get you something better.
And the NRF24 radio operates between 2.4 gigahertz and 2.5 gigahertz. So the bandwidth is 0.125 gigahertz. And if we look at the documents of NRF24 radio, we find the programming resolution of this radio transceiver is 1 megahertz. So that means there are only 125 possible channels. So we have three possible data rates, and we have 125 possible channels. So we can work out the combinations of different air data rate and the channels. So there are a lot of combinations, but it's not impossible to go through all of them to find out the correct settings. And now we only need one more parameter, which is the address of the NRF24 radio. And to detect the address, we need to analyze the error data package format. So this is the error data package used by NRF24 video. And here we can see the data package begin with 1 byte preamble, followed by 3 to 5 bytes address. And after that, it's a 9-bit control field. And then there's 0 to 22 bytes payload. And at the end, there's 1 or 2 byte CRC. And probably this knowledge has been covered in the previous presentation, so I just quickly go through it. So the preamble is used to synchronize the receiver's demodulator to the incoming bit stream, and the preamble is just a series of 0 and 1s. And the address, which is to ensure the receiver will receive the correct data. And the payload is the information contained in the data package, this error data package. So here is the waveform of the error data package from NRF24 radio. And so we can see the transmission begins with a series of 0 and 1s, and in hex number is in this case is AA, so which is just 1010 or 1010. And before this preamble, there's undefined this is a piece of undefined signal, and the NRF receiver will take this piece of signal as 00, hex number 00. So which means the first 2 bytes of one NRF24 data package is always 00 AA or 0055. So all the data package first 2 bytes are the same. Okay. Okay, then so the ideas of detecting the address of one error data package is to set the receiver's address to be 00 AA, so that the receiver can receive all the data packages, because all data begins with 00 AA or 0055. So both of them are working. I have tried both of them are working. Just set it to be 00 AA or 0055. And the problem is, how can we set the receiver's address to be 00 AA, 2-byte address? So if we look at the menu of the NRF24 transmitter, we find the data width can be 3, 4, or 5 bytes. And it's illegal to set it to be 2 bytes. So according to this document, there's no way to set the width of the address to 2 bytes. But we want 2 bytes address. And here we notice some interesting information. It says if you write 00 to the AW receiver, it's illegal. AW receiver is used to control the width of the address. And we tried to write 00 to the AW receiver, and the width of the address becomes 2 bytes. And so we got what we were aiming for. And now we only need to change the address to be a 2-byte address 00 AA. And initially, I made a mistake by following the instruction posted online. And initially, I saw that this 9-bit control field is not important at all. So I just ignored this part. And later on, I found that I was wrong. I'll explain that in the following slides. So if we set the first if we set 00AA as the receiver's address, what will happen? The receiver will receive all the data package, and then it will take the data after this preamble as the payload, because normally it takes the data after the address first 9 bits. It takes the receiver takes it as the control bit, and then it takes the following data to be the payload. But if we change the address to be 00AA, it will take this preamble as the address of the air data package, and then take the first byte of the address as the control field, and then take the following data as the payload. And that's where I made a mistake. So it can be more clear in the next slide. And the first step is to just write a piece of Arduino program to change the width of the receiver's address to be 2 bytes, and then change the address, and then write 00AA to the resistor. And then I got this. So firstly, I just go through all the possible channels. I fix the air data rate at 250 kbps, and then just went through all the possible channels. And I was lucky. I got the correct channel after 10 attempts. And then I received those data. And I thought E7 was the correct address, because in every data package, these 4 bytes remain the same. And I thought that's the correct address. But then I used this address to receive the data from the transmitter. I didn't get anything. If this was correct, I should have received the data sent from the controller, but I didn't get anything. And then I just went back to this air data format, and I made a mistake by ignoring this control field, 9-bit control field. So if I ignore this 9-bit control field, the address will be missing its first byte. So I didn't, in this step, I didn't receive the first byte of the address. So then I just went back to the menu, and I found the NRF24 I used. It uses something called the enhanced soft burst data package. And this one, in order to make it backward compatible with the older versions of NRF24 radios, so this new feature can be disabled. So we can disable the enhanced soft burst and to be compatible with the old soft burst data package. The old soft burst data package doesn't have the 9-bit control field, so we don't need to worry about missing 1 byte in the address. And the manual also tells us how to disable this enhanced soft burst. We just need to write 0 to this ENAA resistor, and then set the ARC resistor value to 0. This ARC resistor's value by default is 0, so we don't need to change anything. We just need to just write 0 to ENAA resistor. And after I did that, I got some new data. And here so the first 5 bytes are consistent in all data packages. So then I know the address should be this E7, 5 E7s. And then I change the receiver's address to be the address I found here, and I received some useful information. And as we can see, the first 15 bytes remain consistent. So I suspect they were the valid payload sent by the receiver. And so to decode those payload, we need to look at the documents of Crazy Fly, the Crazy Fly Zone. In that document, it tells us the commander package. It contains the reference signal for roll, pitch, yaw, and thrust reference signals. And so these 4 reference signals add up to be 14 bytes. And here we received 15 bytes payload. And the first byte 3C is just indicating this data package is a commander is a reference command, and the rest is just the attitude angle reference. And then I changed the pitch angle reference to 30 degree, and the 6th to 9th byte changes. And according to the document, this should be the 4th to 9th byte changes. And according to this menu, the 4th to 7th bytes are the pitch angle reference. So here, when we change the pitch angle reference, the 5th to 8th byte changes. So which means this piece of payload contains the reference signal, and because the first byte is just indicating the type of this payload. Okay, and that's what I have done so far. In the future, I'm planning to write a Arduino script to automatically control the crazy fly zone using our own NRF radio, and hopefully in the future I can find out a way to remotely change the setting of the drone operator's transmitter to disconnect the drone operator from the drone, as I did in the second test. And I'll explore the weakness of RC radios with frequency hopping feature, which is supposed to be harder to attack. Thank you.